Hi everyone, I'm Titouan Carette and I'm presenting here joint work with Dominique Horstman and Simon Perdry. And I will introduce you an extension of SZX-calculus called SZX, S is for Scalable, which is designed to handle registers of qubits. And I will use a running example for this, which is the example of graph states. So what is a graph state? The idea is that you have a graph and you want to construct a quantum state corresponding to this graph. How do you do this? For each vertex, you take a ket plus state, which is a green node in the SZX-calculus, and for each edge, you will apply a control Z gate, like this, and then using spider fusion, we obtain these diagrams. So we see we have a diagrams which is very close to the original graph, and this is what a graph state look like in the SZX-calculus. So now this kind of graph states, they enjoy a very nice invariance property. In fact, if you choose a vertex and you apply a red pi gate on it, and in its neighbors you apply a green pi gate, what happens that you see here, so red is copied, then you have the Hadamard gate, the color change, it slides, and they cancel. So the graph states are invariant by this transformation. In fact, this is an alternative definition of graph states. If you have a quantum state which is invariant by this transformation, then you know that this is a graph state corresponding to your graph. So here we see this is very easy in the X to see why this property is true on a specific example of graph. But how to give a graphical proof which is valid for all graphs? To do this, I will have to draw a diagram like this. So here we see we have a generic J, we have a vertex U, and we have its neighborhood. So now I will do again my transformation. So we see we have copy, then Hadamard, then slide, and then they cancel. So now I'm sure you're all convinced that this is true for all graph states. But if you are convinced, it's because you were able to guess the implicit things hidden by all those dots. And this is something that is not formal enough for a proof graphical assistant, for a graphical proof assistant. So this is a natural question to wonder how to get rid of those dots. And this is not a new question. Numerous PhDs have been done on this subject. And for example, you can use bang boxes. There is a beautiful theory around bang boxes, and you can use them to get rid of these dots. But what I will propose here is something else, something different, which is not stronger or weaker, just complementary. What we do is that we add more types. So usually in the SZX-calculus, we only have one wire type. We just have a wire of size 1 corresponding to a qubit. But what we do here is that we add big wires of size n, and a wire of size n corresponds to a register of n qubits. So we are not in the prop anymore, we have a colored prop, and the colors corresponds to the different sizes. So a little bit of notation. When I write k dot n, this stands for k wires of size n. So here we need to be a little bit careful that if I have k wire of size 0, it's the same thing as 0 wire of size n, which is the same thing as 0, and this is a tensor unit, the complex numbers. So this is not so surprising, but now what might be a little bit surprising that 2 wires of size 1, this is a different thing, very different thing than 1 wire of size 2. Okay, this is the whole point of this construction, but they are indeed isomorphic. There is an isomorphism between those two types. So we have new types. Now let's introduce new generators to construct them. So to construct registers of qubits, so we see we have the divider. So you start from a register of size n plus 1 and you extract 1 qubit from it. Or you also have the gatherer, and here you take a register and 1 qubit, and you will just end up with a register with the size increased by 1. So those two generators satisfy two equations, the elimination equation and the expansion equation. And if you take, so you see those equations are exactly stating that those dividers and gatherer are inverse of each other, and so there are isomorphism. So here we recover the fact that 2 wires of size 1 is isomorphic to 1 wire of size 2. So if you take the graphical language, the colored graphical language, formed by those two generators and those two equations, in fact, this leads to a very simple colored prop. We have this theorem, the rewiring theorem, stating that if two diagrams have the same type, then they are equal. So any well-defined equation holds. So we have nice consequences from this that, for example, this generalized dividers, which extract more than one qubit, it can be defined in a unique way. There is no ambiguity, so we can use it without any worries. Another consequence is that the associativity-like equation is well-typed, so it holds. And then we can define without ambiguity your n-ary dividers and n-ary gatherers. More generally, what we can remember about this rewiring theorem is that as long as you count your qubits, you can do whatever you want with dividers and gatherers. They are very easy and intuitive to use. So now what happens when those dividers and gatherers interact with the usual generators of the SZX-calculus? We have new generators. We call them scale generators. They are just big version of the previous one. For example, here we have a big Hadamard gate of size n. And what happens when it meets dividers, we see that this big Hadamard gate of size n is just in fact the tensor product of n size 1 Hadamard gates. This is the case for Hadamard gate. The situation for spiders is a little maybe more tricky. So we see here, let's not care about the phase first. So we see here a spider of size n is just n spiders of size 1, and we apply them respectively on each qubit in the registers. And now we can do more than just applying the same phases to each qubit in the register. We can index a spider of size n by n phases, a vector or list of size n of phases. And then we just apply the corresponding phase to the corresponding qubits in the register. So for example, here you see ht is a list of phase, and h is a phase, which is the head of the list, and t is a tail, so remember, and you see in this equation, this kind of distribution rule, what happened. So I've had some new types, some new generators, some new equation, and a natural question that maybe you can ask me is, what about the nice completeness result we used to have with the SZX-calculus? Do we still have it? In fact, yes. But we need to extend a little bit the interpretation, the usual interpretation. So now when we have a diagram, it corresponds to a linear map, as usual, but we need this time to keep track of the organization of the data. So we see here the identity on n wires, the identity of size n, is the identity on the Hilbert space, and the type is saying one wire of size n to one wire of size n. This is the same for the Hadamard gate of size n. You see, it's just the tensor product of n Hadamard gate, and it sends one wire of size n to one wire of size n. A more interesting case is the interpretation of the divider. Here we see this is the identity on the Hilbert space, but a divider changes the organization of data because it sends one wire of size n plus 1 to one wire of size 1 and one wire of size n. So I give you also the interpretation of the spider. But the main thing to remember is that inside SZX, the generators from the SZX-calculus are just acting on the Hilbert space and are not doing anything on the organization of qubits. And on the other hand, the generators, dividers, and gatherers are not doing anything on the Hilbert space, but they do change the organization of data. So the action is kind of orthogonal to each other, and we can see this in this kind of normal form I'm showing here, because any diagram of SZX, you can use the rewriting rule to write it in this form. First, you divide everything into wires of size 1, then you apply generators of size 1 of the SZX-calculus, and finally, you just use gatherers to form the register you want to form. And with this normal form, you're able to recover your completeness result from before. Okay, so this is all I have to say about completeness. Now, let's see what we can do, which is new with this SZX. Another thing we can do, it's possible to write in a compact way large-scale structure. So we see what happened with bipartite graphs. So we have some bipartite graphs between green and red nodes. And here you see this A is a 0-1 matrix stating which green node is connecting to which red node. So A is a B adjacency matrix of the bipartite graph. So we have some scalars here, and they're just here because we are not clever enough to choose the right normalization, but they are not important. They are just here for the sake of exactness. But I will not care about them in the remaining of my talk. And then we can use dividers and gatherers to box this bipartite graph. And this is definition is what we call a matrix arrow indexed by a 0-1 matrix A. So here, A is of size n by m and not 2 to the n by 2 to the m. So this A is not just going back to linear algebra from the SZX-calculus, but is a clever, compact way to represent a bigger diagram. So in fact, why do I care about the matrix arrows? It's because their interpretation is very nice. In fact, it's just applying the 0-1 matrix A to the 0-1 vector of the basis. So from a practical point of view, for example, a secret made of C-nodes is of this form, and most of the encoding and decoding map in a contour mirror correction are of this form too. So now, in this definition, you see again those ugly dots, but it's possible to get rid of them because there is an equivalent way to speak about those matrix arrows. This is to define them inductively with those 4 axioms. And from those 4 axioms, you can show this bipartite representation. So this is not a definition anymore, but a theorem. And from those axioms, you can derive other nice properties. For example, 2 matrices compose with matrix multiplication. You can also copy them and erase them using green dots. You can add them. So here's this addition in F2, 1 plus 1 equals 0. You can add them with this diagram. This is very useful in practice that here V is a 0-1 vector. Okay, so this pi V is a generalized phase, red phase, and when it goes through A, then you just apply A on V, in fact. This is very useful. So now when a matrix arrow goes through a Hadamard gate, then you reverse the direction of the arrow and you take a transpose. And using this equation, you are able to give a color swap version of all the equations in the first row. And this gives you this. So here, let's try to interpret this a little bit. For example, with the red node here, if you interpret the red node as an addition in F2, you see we are just ensuring linearity here, saying that A is linear. And then you see this is a co-erasement. In fact, it's just stating that 0 should be in the kernel of A, which is always the case because A is linear. I will take a little more time of what happened with generalized green phases. Because here what we see is that if you have this 0-1 vector U going backwards through the matrix, then you just take the transpose of the matrix and the U. Okay, so that's all I have to say about matrix arrows. Let's come back to graph states. This is a graph state. So it might be not so obvious to see why. So we will just open the matrix arrow. So we see we open it. The Hadamard goes through the divider. Then it changes the color. So we go from red to green. And here, I think it's clear. We see this is a graph state. But it's possible, in fact, that any graph states can be written in this form. How to do this? For the gamma, you just need to take a upper triangular matrix, which is in fact half of the adjacency matrix of J. So for this fact, you need not to believe me because we can check this. We know that there is an alternative definition of graph states using invariance properties. So let's just check this invariance property on this graph. So we take gamma, as I say, this is half the adjacency matrix, and let's go. So here we see this U is a 0-1 vector, which is 0 everywhere except on the wire corresponding to the vertex U. So this generalized phase here is exactly just sending a pi gate, red pi gate on the vertex U. Now, by definition, the adjacency matrix is equal to gamma plus gamma transpose. It's a symmetric matrix. So the neighborhood of U is exactly gamma plus gamma transposed applied to U. So this generalized green phase here is exactly sending green pi gates to all the neighbors of U. Okay, so now let's compute and see if it is invariant. So first we copy, then we go through the Hadamard gate, so we change the color, and then we are going backward into a matrix arrows with the green generalized phase, and then we take the transpose of gamma. Now, those two generalized phases, the green and the red, we see that since U is not a neighbor of U, then they are acting on different wires, and so they commute. And finally, using spider fusion, we can cancel those two gamma transpose of U. Now it only remains to take care of the last red generalized phase, and we see it goes this time in the right direction through gamma. This take a gamma. It goes through the Hadamard gate, so we change the color, and finally, using spider fusion, everything cancels. So it's done. In fact, this is a graph state. And what you just saw is the same proof as before, but without any dots. We managed, using the scalable calculus, to get rid of the dots. So there is other proofs I can do this way with this representation of graph state. For example, we have a proof of local complementation or pivoting. We are also working on other representation. For example, some algorithm. We have some quantum algorithm which are nice in this representation, and some others we are still working on them. Good. Now to conclude, nothing of what I said is ZX dependent. In fact, if you take any graphical language, any prop, you can add dividers and gatherers and new types, and then you end up with a colored prop. Then if at first you add a completeness result using the same extension of the interpretation that I gave, you still have your completeness result. Okay, so this is not ZX dependent, this is a very general construction. You can do scalable props in general. In this setting, the general setting, what happened with matrix arrows is just that we use the fact that there is a model of interacting up algebras into SZX-calculus. And we knew that interacting up algebras are complete for those F2 matrices. So in this way, we see that it's not a surprise that we have all those nice linear algebraic row, writing row, because we knew that AH was complete for. So what can we do if we extend this thought? Then if we have two languages that have nothing to do with each other, but if we have a model of one into the other and a completeness result, and we can use this completeness result to draw diagrams in a compact way. And if we think along this line, we can interpret that the spider notation, in fact, spider notation, we can see it as just a clever notation for correlation, and we know that correlations are complete for extraspatial Frobenius algebras. So this is another way also to see some previous notation, and I hope there are other examples that will arise sooner or later. And my last general remark is that what we have done here is just to add more type and generators with no action at all on the Hilbert space, but only here to add more expressivity about the organization of data, about data structures. Here, we have done it with a very simple data structure, just registers of qubits. But I'm sure that it's possible to use the same construction for more complex and more interesting data structure, and we'll see this in future work. So this is the end of my talk, and I have nothing more to say. Thank you for your attention. If you have any question, you can ask them in the Slack or send me emails if you are shy. Do whatever you want. And since after all, we are in Paris, je vous remercie beaucoup pour votre attention. Au revoir.